Well, hello everybody. Welcome to another lecture for Math 300. So just to remind us that last time what we talked about was... Anyway, last time what we talked about was proof by induction. And so what we saw was that if we can prove something for a base case, then what we get is that we get to assume that something's true for the nth case, and we have to show it's true for the n plus 1 case. Then what happens is, well, because it's true for the first case, it's then true for the second, the third, the fourth, fifth, and so on. And so we get that our theorem will be true for all natural numbers. Where we left off last time is we went through some examples, and today what we're going to do is we're going to start off with strong induction. So the distinction between regular induction or weak induction and strong induction is just that instead of assuming that things are true for the kth case, we're going to assume that it's true for the first, second, third, fourth, all the way up to k. So if we look at that back in our last example, the idea was we would prove it's true for the first case, and then we would do something like assume it's true for 1, 2, 3, and 4, and then show that it has to be true for the fifth case. Well, if we do this in general, the first case implies the second, then the first and second implies the third, and then the first, second, third implies the fourth, and then the first, second, third, and fourth implies the fifth. And so again, you will get that this is true for all natural numbers. And so the only distinction here is that we're assuming it's true for the 1, 2, 3, all the way up to kth case, and we have to prove it's true for the k plus 1 case. So we just work with more numbers than directly just k. Now, how is that going to come into play? Well, let's look at an example here. Let's suppose that I want to show that for all natural numbers with n greater than or equal to 8, there exists a non-negative integer k and l such that 3k plus 5l is equal to n. All right. So what we're going to do here is we're going to start off, and our base case is 8. So if we let n equal 8, we get 8 is equal to, and now I have to find a k and l. So I'm just going to say this is 3 times 1 plus 5 times 1. And so I found k and I found l. Therefore, there exists a k, there exists an l, such that 8 is equal to 3 times k plus 5 times l. And so we have it for our base case of 8. Now, if we try to look at our general case, what's going to end up happening here is that we're actually going to need more base cases than just n equals 8. And we'll have to figure out how many base cases we need as we get there. And so we're just going to start off and say, okay, well, let's assume that by the induction hypothesis that if m is equal to 3k plus 5l for 8 less than or equal to m, and we have to show that m plus 1 is equal to 3k plus 5l. So let's say, I need another letter, so let's just say j. And so the idea behind a strong induction is that we get to assume that this is true for everything between 8 and j, and then I have to show it's true for the j plus 1 term. I was using k in my definition, but because I'm using k in my theorem, I don't want to reuse it. So I made a new letter up. So I get to assume that it's true for up to here to here. Now, how would I show that j plus 1 is equal to 3k plus 5l for some integers k and l? Is I'm going to have to work with this somehow. And so what we notice is that, well, if this is 3k plus 5l, this is some integer and this is some integer here, what I can do is I can say this is what I want to show. So what I can do is I can say j plus 1 is equal to, well, j plus 1 minus 3 plus 3. And why am I doing that? Well, what happens is that this term is just going to be j minus 2. And then the next term is just a 3. So what happens is I want to write it in form of 3 times something and 5 times something. So if I start with j minus 2 and then add 3, well, I'm factoring out a 3 here, so it's okay just to have an extra term here. So, but now if I look at j minus 2, notice that j minus 2 is actually less than j. So, assuming that j minus 2 is bigger than or equal to 8, we get that j minus 2 falls into this case. So the point here is that last time we would just get to assume this is true for j, but here we want to assume it's true for j minus 2. And so if I use the induction hypothesis, what I get is that j minus 2 is 3 times, let's say, k1 plus 5 times l1 plus 3 for some integers k1 and l1 by the induction hypothesis. But then if I put this together, I get 3 times k1 plus 1 plus 5l1. Because I have a 3 here, I add them together, I get 3 times k1 plus 1. And so if I let, say, k2 be k1 plus 1, I get that I have now rewritten j plus 1 as 3 times an integer, which was our k1 plus 1, plus 5 times an integer. So we get that, assuming this is true for 8 up to j, we get that 3k2 plus 5l1 is indeed, our j plus 1 can indeed be written in that form. Now what I want to point out here is that this was based on the assumption that j minus 2 would be greater than or equal to 8. So what does that mean is that, well, that means that I can't just use 8 as a base case, because if I pick 9, 9 minus 2 is 7, is not in there. So I would have to show 9 as a base case. If I use 10, well, 10 minus 2 is 8. So then this would follow because 8 can be written in this form. Or, I'm sorry, if j was 10, notice we're taking actually j plus 1. So if j is 10, we get that 8 would be here, but we're trying to write 11 in this form, and so we would need, in this case, 11 minus 2 is 9, so that would not be in there. So the point is I'm trying to work with j plus 1. So if j is 8, this gives me 9. 9 minus 2 isn't working. If I have 9, 9 plus 1 is 10 minus 2, that's not working. If I plug in 10, I get a 10 is 11 minus 2 is 9, so that works. And so what I have to do is show this not only for the case of 8, but I also have to show it for 9 and 10 to make sure I get far enough that this j minus 2 is still going to be appropriately within this range. All right. So what that means is just I have more base cases. So I have to show it's true for 8, which we already did. And so we'll say, okay, well, let's let n be 9. Can I write 9 as 3 times something plus 5 times something? Well, this is 3 times 3 plus 5 times 0. And 10 can just be written as 3 times 0 plus 5 times 2. So now we have, okay, this is true for 8, 9, and 10. So now if I try to do 11, I can end up subtracting 3 from 11 and get 8. So I can do 8 and add a 3 to it. If I try to do 12, I can subtract 3 from that and get 9. And so I can add another term to 9, so I can do 12. I can do 13 then, and 14, and 15, and 16, and so on. So we get that this would have to be true for all natural numbers. Now, just to recap then how I would write this up is once you get done with it and realize your base cases, you should write your base cases first. And then you could assume that it's true for 8 up to j, and then show it's true for j plus 1. And so if I subtract 3 from j plus 1, I have to ensure that I'm bigger than 8. So that's what the base cases will cover, and then I can go through the proof that I had before. Are there any questions on that at all? Alright, so just to point out, when you guys are looking at the homework, the strong induction proofs will look similar to this one. And so try to work with things like these and get used to those. What I wanted to do though is I wanted to show kind of the utility of strong induction by looking at some different proofs that are more useful in general. And so what I want to look at is the fundamental theorem of arithmetic. Anytime you say a fundamental theorem, it just makes it sound important. So yes, this is an important one. What does the fundamental theorem of arithmetic say? Well, what it says is that each natural number can be uniquely factored into primes up to a rearrangement. So what does that mean? Well, it means if I take any natural number, I can rewrite it as a product where each of the terms are prime. Furthermore, I can do this in such a way that up to a rearrangement, there's a unique way to do this. So for example, I can write 6 as 2 times 3 or 3 times 2, but the only way to write it as the product of primes is involving a 2 and a 3 in some order. If I write 7, well, 7 is prime, so it's already written as a product of primes, and 8 is 2 times 2 times 2, so that is the only way we can write 8. So what we want to do is we want to show that this is true for all natural numbers. And there's actually two things involved here. First off, we have an existence proof. That is, we have to show that it is possible or there exists a factorization of any natural number. Secondly, then we need to show that such a factorization is unique. So hidden in here, there's both an existence and a uniqueness proof. So we'll have to do both of those. So we're going to start off with an existence proof. Alright, for an existence proof, we're going to proceed by induction. And I do want to point out that this should be all natural numbers greater than or equal to 2 because 1 can only be written as a product of 1 if I'm using natural numbers. So that one can't be written as the product of primes, but other than that, all natural numbers can. So my base case is here going to be 2, as if n is equal to 2. So then I can write 2 as the product of primes just by writing 2 is equal to 2. Notice that 2 is prime, therefore I've written it as a product of things using only prime terms. Alright, so now what I'm going to do is I'm going to use my strong induction, and I'm going to assume that if k is a natural number, then k can be written as a product of primes. And that is, I should say, and then I want to show that suppose k is in here, and let's say 2 is less than or equal to k is less than or equal to m. Then we want to show that m plus 1 can be written as the product of primes. So because I'm using strong induction, I'm going to say that, okay, by the induction hypothesis, we're going to assume that we can write any number between 2 and m as the product of primes. And so we have to show it's true for the m plus 1 case. Now, let's actually look at this. So what I'm going to do is I'm going to take m plus 1, and I'm going to try to factor it so that all I have are primes in the terms. Well, what could happen is m plus 1 could be prime. Because this is a natural number, it could be prime. If m plus 1 is prime, then we're done. So, if m plus 1 prime, we are done. Meaning that we have written m plus 1 as the product of primes by just writing down m plus 1. So, there's nothing to prove there. We have our statement. We don't even have to use our induction hypothesis. We just get this as prime, so we're done. Otherwise, what we're going to assume is that m plus 1 is not prime. So therefore, what we get is that m plus 1 is not prime. So what I can do is, well, because it's not prime, it means that it has a factor other than 1 in itself. So let's call that factor a. So this is divisible by a for a strictly greater than 1. And we can even say, be more precise, 1 is less than a is less than m plus 1. Because if a is a divisor, it has to be less than or equal to m plus 1, but we're assuming it's not equal because we're showing that this is not prime, so this is one of the divisors other than 1 and m plus 1. Well, that means that m plus 1 is equal to a times some integer, so let's say that integer is b, and what we get is, because m plus 1 has a divisor other than 1 in itself, I can rewrite m plus 1 as a times b. Alright, we're getting somewhere. Now, what do we do next is, notice that we just said 1 is less than a is less than m plus 1. Therefore, a satisfies the fact that it is between 2 and m. So that is 2 is less than or equal to a is less than or equal to m. So this, by our induction hypothesis, can be written as the product of primes. So, by our induction hypothesis, a is equal to some prime 1, prime 2, let's say prime L. However, what we also get is that since b is here, a times b is m plus 1, b also divides m plus 1. Since a is bigger than or equal to 2 and less than or equal to m, we have to get that b will also have to be in that range. Because if b is, say, m plus 1, that would force a to be 1, which is not true. And if b is 1, then a would be m plus 1 is not true. So b has to be strictly between those. So, by our induction hypothesis, b is also equal to the product of primes. Let's say q1, q2, up through q sub, now let's use a letter h. But what have we just done is we've said that m plus 1 can be written as a times b. Therefore, m plus 1 can be written as a, which is p1, p2, pl, times b as q1 through qh. So what we've done is we've actually written m plus 1 as the product of primes using our induction hypothesis. Because a is somewhere less than m plus 1, we can do that. B is less than m plus 1, so we can do this as well. So we have these are written as the product of primes. We substitute in, and we get exactly what we're looking for. Therefore, if m plus 1 is prime, we're done. If m plus 1 is not prime, then we can factor it into smaller terms, and each of those smaller terms by the induction hypothesis can be written as the product of primes. Therefore, well, we know it's true for the second case, which implies it's true for 3 and 4 and 5, and so 2 and 3 imply 4, 2, 3, 4 imply 5, 2, 3, 4, 5 imply 6, and so through induction we get that all natural numbers can be written as the product of primes, so we have an existence of this factorization. We still haven't shown uniqueness, but we have shown existence. So any number, any natural number can be written as the product of primes. All right. Now, what we're going to do is, we're also going to use an inductive process here, but what we're going to do is, let's assume that we have a natural number. So let n be a natural number. We know that we can write n as the product of primes, we'll say p1 through pm. But let's suppose that n can also be written as the product of primes q1 through qk. So I'm not even going to assume that these are the same number. I'm just going to assume that I can write it in two different ways. I know that I can write it in at least one way because I've already shown existence. But if I can do it in two ways, I want to show that these two things have to actually be the same up to a rearrangement. So the point here is that P1, P2 through PM is equal through Q1 through QK. So this product is equal to this product. Well, what do we notice here is that this is an integer. Okay, how is that helpful? Is that, well, that means that P1 divides Q1 through QK. So therefore, P1 divides a product of terms. If you guys recall on Wednesday, what did we show is that if a prime divides a product of terms, it has to divide one of the terms. Therefore, P1 divides Q sub I for one of the Q sub i's in this term. So I'm going to say implies. Now, remember that these are all primes, right? So if P1, which is a prime, so it's not 1, divides Q sub I, what does that mean? Well, Q sub I is only divisible by 1 in itself. Since P1 is not 1, this implies that P1 is equal to Q sub I. So therefore, what we've got is that if I have P1 through PM and Q1 through QK, I have a P1 here, and somewhere in here, it's probably not Q1, it's one of the terms, there's going to be a P1. So what can we do is we can cancel the P1s out, and so what I'm left with is P2 through PM is equal to Q1 through Qi minus 1, Qi plus 1 to Qk. So that is, I factored out the P1, and I'm left with the new term. Now I do the same thing for P2. P2 then divides this term, so it's equal to one of these terms. Now I'm kind of setting up the induction process here, is that, okay, P2 is equal to one of these, so I can cancel out the P2, and then the P3, and then the P4, P5, all the way up to PM. And so if I've canceled out P2 all the way up to PM, what I'm going to be left with is 1 on this side. And so what I have to have left over here is 1. So each time I was able to factor, I was able to take out one of the terms. In the end, I end up with no more primes left. So I have to have exactly the same number of primes, because at exactly the same point after factoring, I'm going to get 1 left. Also, each one of these is the same along the way up to a reordering, meaning they might be in different places. But we get that P1 is equal to Q sub I, P2 is equal to Q sub j, P3 is equal to Q sub something, and every one of these is equal to one of these. So you have to have exactly the same number of terms, and each of the terms has to be exactly the same. So what does that mean? Well, that means precisely that we have just shown the fundamental theorem of arithmetic, that every product or every natural number can be written as the product of primes in a unique way. All right. Did anybody have any questions on that? All right. On the last thing I want to do, I didn't have up here on the PowerPoint, But I wanted to show one more proof by induction, and that is I want to show that the cube root of 2 is not constructible. So now I haven't used this word before, constructible. What does that even mean? Well, where this problem comes from is this is actually an ancient problem, and it comes from, well, during a plague, of all things. So, the situation not too different from what we have is that, except for much worse. So back in ancient Greece, about 200, 300 BCE, I'm not sure exactly, but somewhere in there, there's a huge plague, and it's wiping out a third of the population of Greece. So, what do the Greek people do is they go to the Oracle of Delphi and they ask her to have Apollo intervene on their behalf to save them all. Seems like a reasonable thing to do. Alright, so the Oracle of Delphi said, you currently have a cubic altar for Apollo. If you make one that is exactly double the size, then he will intervene and he will save everybody else. Well, they went out and instead of having whatever length it was, they doubled the length of the altar. And so, but since it was a cube, that means that they've now made it 8 times as large. And so when they went back to the Oracle, she said, no, you made it 8 times as large, not twice as large, so that is not fine. I wanted it twice the size. So they went back, and the idea is that if I want to take a cube, here's a cube, and I want to make one which is exactly twice the volume, what I need is my new length. Instead of being 1, this should be the cube root of 2, because if I take the cube root of 2 cubed, that will be exactly double the volume, because cube root of 2 times cube root of 2 times cube root of 2 would exactly be 2. So we assume this volume is 1. That means that this volume would be 2. Alright, so there's where this problem comes from. It is one of the problems of antiquity. And we're going to prove it, even though it took mankind like 1800 years to do it. It's a fun proof. Now, what does constructible mean? Well, at the time when they were trying to start off with 1 and get the cube root of 2, the only tools they were allowed to use were a straight edge and a compass. So they could use a ruler to draw a straight line, and they could use a compass to draw a circle. Alright, so using a straight edge and compass, they needed to come up with this. Why? Well, because they considered these to be exact tools, therefore you could exactly find the distance. And in order to be good enough for a god, it has to be exact. It can't be an approximation. If they wanted to, they could have easily found an approximation for the cube root of 2, but that wasn't good enough for the gods. Now, to skip over a lot of this, but if you take modern geometry, you can go through and find all this. The idea is that using straight edge and compass, I can find a number if, starting with 1, I can do things like add, subtract, multiply, divide by a non-zero number, and I can take square roots of non-negative numbers. So what I get is any constructible number can be starting with 1. I'm going to close it under addition, subtraction, multiplication, division, and by non-zero numbers, and square roots of non-negative numbers, and that's going to be all of my constructible numbers. Therefore, what I end up with is what would be called the field. So a field would be closed under products, sums, additive inverses are differences, products, and multiplicative inverses are divisors for non-zero terms, but we also get this extra square root thing. Alright. So now, if we want to point out, is that if I start with 1, I'm going to say that the smallest field I can create using one is the rational numbers. And actually, if you want to see that, I do have a post on my website about the field generated by 1 will give me the rational numbers, so you can see why that's true. But I'm going to leave that up there as just saying that that's going to be the case. So my smallest field containing 1 is the rationals. So what I want to point out is that if anything is in the rationals, it is constructible because I can find it using sums, differences, products, and quotients. I don't even need square roots here. So if I can get the cube root of 2 as rational, then it is indeed constructible, so that's a counterexample. So the first thing I have to show is, this is going to be my base case, is that the cube root of 2 is not rational. So the cube root of 2 is not a rational number. Now, we've actually done this one earlier in the class, but to recap, the idea is that we would assume by contradiction that it is rational. So we get the cube root of 2 is p over q. So if I cube both sides, I get 2 is p cubed over q cubed. So 2q cubed is p cubed. Hence, 2 divides p cubed, because 2 times q cubed is p cubed, so p cubed is going to be even. But we know that if 2 divides, 2 is prime, so it divides product of terms. It has to divide one of the terms, but all the terms here are p times p times p, so that means that 2 divides p. Hence, p is even. So p is equal to 2 times, let's say, k for some integer k. Well, that means that 2q cubed was equal to 2k cubed, which means that 2q cubed is equal to 8k cubed. And if I divide by 2, I get q cubed is 4k cubed, or 2 times 2k cubed. So what does that mean? Well, it means 2 divides q cubed. So 2 divides q for the same reason as it did before. And so what I get is that if the cube root of 2 is rational, then both p and q must be even. Now, if you remember back to when we did the square root of 2, we said, well, if both of these are even, we could factor out the 2. And if they're still even, we could factor out the 2. And if we keep factoring out the 2's, eventually one of these has to be odd. So if both of these have to be even for this to be true, well, eventually I can simplify this until one of these terms is odd. So what we get here is a contradiction, because this is saying that we couldn't do that. We couldn't always get an odd and an even, but we know that we can always simplify till we get an odd and an even. So we get a contradiction to the fact that cube root of 2 is rational, which implies then the cube root of 2 is irrational. So there's a recap of what we've shown when we're talking about the square root of 2. We're just now using the cube root of 2. All right. So now what I'm going to do is I'm going to say this is f sub 0. And so I've shown the case that the cube root of 2 is not an f sub 0. What I want to do is I want to do an induction proof by contradiction to show that then it cannot be in any of the next ones. So what that means is I want to show that, okay, if it's not an F0, then it can't be an F1. And if it's not an F1, it can't be an F2, an F3, up to whatever, so that I can't be in F sub n in general. And what I'm going to say here is that, well, so far what I used was sums, differences, products, and quotients. And so now I have to introduce a square root. So what I'm going to say is f sub 0 is going to be, or f sub 1 is going to be f sub 0 closed under square roots of non-negative numbers, just using them once. So I can use one square root. So what does that mean? Well, that means that I can take anything of the form a plus b times the square root of c, where a, b, and c are in f sub 0. So I can use one square root, I get A is in F sub 0, B is in F sub 0, C is in F sub 0. I'm still allowed to add, multiply, subtract, and divide, but because these are all closed under that, all I really need to say is all these things are going to end up looking like A plus B square roots of C. And so if I add one square root, that's what I'm going to get. In general, I'm going to say F sub n is equal to F sub n minus 1, or is equal to A plus B square roots of C, where A, B, and C are in F sub n minus 1. All right. So the idea is that I'm going to inductively define these things, and I would say F sub 0 is this, F sub 1 is this, F sub 2, F sub n, and then I would claim that all constructible numbers are, well, I can find those by using some finite number of square roots. So this is going to be the union of all n in n of my F sub n's. So if I want to find all constructible numbers, I take the union of all natural numbers of the F sub n's. So that is, I have to do this finitely many times. So that's how I'm going to define my constructible numbers. And so now I need to show that this is not in here. All right. Hence, I said I was going to proceed by contradiction. So if I'm going to proceed by contradiction, I'm going to assume that cube root of 2 is constructible. Since my constructible numbers were all of the F sub n's for n and n, what that means is then the cube root of 2 has to be in F sub n for some n. So there is some natural number such that it would be in F sub n. Notice that if it's in F sub n, though, the way we defined it is that it would have to be in F sub n plus 1, plus 2, plus 3, plus 4, and so on. And so once it's in F sub n, it's in all of them after that, but not necessarily before that. All right. So what ends up happening here is that if we assume it's in F sub n, that means that I can write the cube root of 2 as A plus B square roots of C, where A, B, and C are in F sub n minus 1. Any questions so far? I haven't heard or seen any statements. All right, I will continue with this then. All right, so what this means is, well, I can actually cube both sides, so I get 2 is equal to, and if I cube this side, I get A cubed plus 3A squared B squared C plus 6A, plus 4A, this is B square roots of C, 4A times this squared would be B squared C, plus 3 times, oh my goodness, I'm sorry. I'm trying to do this at the board. I'm going to make mistakes. I'm going to use my Pascal's triangle. There we go. That was the problem. I was trying to add an extra term in, but it should be 1, 3, 3, 1. So it should be A cubed plus 3A squared B square roots of C plus 3A B squared C plus B cubed square root of C cubed. So I'm using the binomial theorem here. I cubed this term plus 3 times this term squared plus this term plus 3 times this term squared plus 1 times this term cubed. And now if I cube this, what I'm going to notice is that there's some square roots of C and there's some not square roots of C. And so I'm going to group these so that I get 2 is equal to A cubed plus 3AB squared C plus 3A squared B and plus B cubed C times the square root of C. All right. I'm going to need more room, so I'm going to come up here. And the next thing I'm going to do is I'm going to say that, well, I can subtract 2, and I get 0 is equal to a cubed plus 3ab squared c minus 2 plus 3a squared b plus b cubed c times the square root of c. All right. Now, just to make things easier, there's lots going on. So I'm going to call this capital A, this capital B. And so I'm just going to rewrite it as A plus B square roots of C. Now, what I want to point out here is that let's assume that B was 0. If B was 0, then what I get is that 2 is equal to some rational number plus the square root of C. And so if C was 0, then what I would get is that the cube root of 2 is equal to A plus B square roots of C. So if this was 0, this would turn out to be 0. So the cube root of 2 would actually be an f sub n minus 1. So we'll keep that in mind. If C is 0, then the cube root of 2 ends up being an f sub n minus 1. So let's suppose that the square root of C is not 0. Then what I would get is, well, negative A is equal to B square roots of C. And now, if this was non-zero, then what I would get is I could divide by it. So I get negative B is equal to the square root of C. But notice that this is an f sub n minus 1 because these terms this is closed under products and sums. This term is an f sub n minus 1. So that implies that the square root of C is an f sub n minus 1. So if the cube root of 2 is equal to A plus B square roots of C, each of these are an f sub n minus 1. That implies that the cube root of 2 is an f sub n minus 1. So if C is 0, cube root of 2 is in the previous one. If B is non-zero, then the cube root of 2 is in the previous one. So what that means is that B has to be 0. Therefore, we get 0 is equal to A plus 0 square roots of C. And so that implies that A is also equal to 0. All right. Now, why is that helpful at all? Well, we'll see. But we do know that if this was 0, then we would be in our previous term. If this was non-zero, we'd be in our previous term. So the only way that we could not be in our previous term is if B was 0, C was non-zero. And so we get A must be 0. And so the point is that we said that the cube root of 2 is equal to A plus B square roots of C as a solution. But this term here has to be 0. This term here has to be 0 when we're done. Now, the reason why that's going to be helpful is because if I take A minus B times the square root of C and I cube it, just for the sake of time, I'm not going to do this arithmetic for you. But if you do this, what you end up with is, and I subtract 2, what I get is A minus B square roots of C. All right. So what that means is, well, this was 0 and this was 0. So this is equal to 0. So what that means is that A minus B square roots of C cubed minus 2 is equal to 0. If I then add 2 to both sides, I get this cubed is equal to 2. Therefore, a minus b square roots of c would have to be another cube root of 2. So that is, if I have the cube root of 2 is a plus b square roots of c, then also I have that a minus b square roots of c is also a cube root of 2. However, what we know is that this then implies that there would be 2 answers, but if we look at the cube root of x, it looks like this. The cube root of x is an increasing, always increasing function. Therefore, there is only one real solution to the cube root of 2. Therefore, I can't have 2 unique solutions. So what I would have to have is the only way these could be equal is a plus b square roots of c is equal to a minus b square roots of c, as if I could subtract a. If I add that over, I have 2 of these is equal to 0. So that is, this term would have to be equal to 0. So I found 2, but I know that there can only be 1. So therefore, 2b square roots of c has to be 0. But if that's 0, then this is 0, which implies, again, that the cube root of 2 is in f sub n minus 1. All right. So now let's recap. What did we have is we knew that the cube root of 2 is not rational. So if it was constructible, it had to be in f sub n for some n. However, what I've just proved is that if it's in f sub n, that implies that it's in f sub n minus 1. But using the same proof, that would imply it's in f sub n minus 2, all the way down to my base case, which would be f sub 0 or q. So inductively, we get that if it's in any f sub n, it's in the previous one. Therefore, it would have to be rational. So that's the inductive step here. But we know that it's not rational because we've already proven that. So therefore, the cube root of 2 cannot be in any f sub n because it's not in the rational numbers. Therefore, the cube root of 2 cannot be constructible. Hence, we get our theorem that the cube root of 2 is not constructible, or is not an element of F, the field of constructible numbers. Now, the reason why I like to point this one out is it's a really fun proof. I enjoy it. You get some field theory in there, and you get some field extensions and things like that that you'll see in abstract algebra. But the biggest thing was that the problem or the question arose in antiquity over 2,000 years ago, 2,200 years ago. However, we're using things here that weren't discovered until the 19th century, or weren't talked about until the 19th century, such as fields and field extensions and other things like that. So this theorem, this question, can I find the cube root of 2, was not shown for 19 or 2,000 years basically after the question was asked. And I just want to point out that's a really great question if it takes that long to solve. But if it took that long to solve and our answer is we cannot do it, what does that mean for the Greeks? Well, that means that they were not able to make an altar of the correct size for Apollo. So Apollo did not help them get over the plague. Very sad story. So they had to suffer through the plague, and lots more people died. That seems very depressing. Now, if you try to say, well, why in the world would a priest send you home and tell you to do something impossible? So if you assume that Apollo would know that this was impossible, or the Oracle of Delphi would know this is impossible, why would they send them home to do it? Well, what Plato said is that in this time of plague, what you guys should do is go home and do some math. So you should go home and do some math and stop fighting each other and stop killing each other and stop spreading disease. So, just a note for you guys, if we follow that, that means that right now what we should be doing is staying home and doing math, which is what we are doing. That's how amazing math is. All right. There you go. There's my historical story for you. I will not ask you to repeat that proof, but I just think it's such a cool story that I had to do it for you. Do you guys have any questions before I let you go? Well, seeing none, I will just say thank you guys for joining me. I hope you enjoyed today's lecture. And I will see you on Monday. The goal for Monday is I do have the homework posted already. So please do the homework for Monday. And I plan on just going over the homework with you. So answering any questions you have. So if you go over it and you want to look at this or that, please let me know in the chat on Monday. And then we'll spend time doing that. Hopefully you guys have questions. Otherwise, I'll have to find something else to talk about. But have a great weekend.